And thank you, Maggie. So, but before we do that, we've got a little housekeeping to do, and not the least of which is Hasna's birthday. And we have a special birthday song. Let's see, I've got to go find it. Oh, Mark, it's scrolled up on my chat, and I can't find it again. Although I think I have it. Which one did you have, or can you? Ah, there it is. All right, great. So I'm gonna open that.
Hopefully it works. I can't remember. I might have posted it in the Slack channel.
Yep. No, I got the link, and I'm just gonna share my screen again, and I'm gonna try and share my screen again. Where is it? Okay, share. There we go. All right, great. So this is from the Curiosity rover. Feel free to unmute yourself and join in to Happy Birthday for Hasna. Happy birthday to you. Happy
On August 5th, Husqvarna is launching a software update, giving our robotic lawnmowers a voice to sing happy birthday to the loneliest robot in the universe.
Almost makes me want to go buy a lawnmower from him.
So so now I'm really curious though. Is the Happy Birthday song like universal? Has it been adopted, or what would you, so Hasna, what would you would you sing something in Egypt, or is there something different you would sing in Egypt?
Yes, not very different actually. We usually use happy birthday song in English words sometimes, and in addition to that, we have some funny songs with funny animals, and we usually sing these songs with the children. So it's a little bit funny.
Okay. All right. Well, maybe you can share some of that in chat if you've got a recording someplace of it, or it's on YouTube or something. Anyway, happy birthday. I'm glad that we could spend it to you. I hope that we are not intruding too much on your special day for this, but and we'll spend it talking about some science, and then and okay, so two other housekeeping notes. So Maggie, so Maggie has been collecting as best she can the presentations. I know that I'm behind. Not that my presentations are brilliant, and at least one of them I can't share because it's not mine. If the other presentations from the guest speakers have been, Maggie has been collecting in a shared folder, and she has just posted it on Slack under the, which channel is that?
General.
General channel. Okay.
Mhm.
So you should be able to go look at the shared folder and see in the general channel. In the general channel, you should see the shared folder, and you should have access to that on Slack. Can somebody give me a thumbs up if that works for you? Great. So, okay, good. So a bunch of people are saying that, give me a thumbs up, and they can see some of the presentation. Some of them are empty, but we'll see what we can do about filling them up. So great. The other piece of housekeeping is, I gotta find it. It's here. I just wanted to share with you, we did the quick survey that we did over the weekends. So just to get really do a check-in and make sure that we're more or less on target. So about 75% of you say that 75% of the people who responded, which is about half of you responded to the survey. 75% of those who responded say that we are meeting or exceeding expectations. So that's good, but we can do better, and we will endeavor to do so. And we've been looking at your comments, both the good and the bad. And just as another quick update, so more than half of you have said that you are happy with the time zone group as it is right now, and only a few are having or want to, I won't say you're having difficulties, but want to change your time zone groups. I hope those haven't been, for those of you who want to change, those haven't been too difficult, and I would continue to encourage you to work together to explore some of the materials that we've been giving you, including both the labs and some of the reading. Use it as a study group as best you can, and try and make sure that you're supporting each other, not only supporting your own learning, but also making sure that other people understand what and have questions or discussion, and in those groups you should be listening. Since they're groups of 4 or 5, you should be listening about 70 or 80% of the time, and talking about 20% of the time, just to make sure you're listening as much as more than you're talking. Great. So that's a result of the survey. You will have an opportunity at the end of the workshop to give us more extensive feedback on a wide range of things that we've done, and both through we want to run a little bit of a discussion at the end, and also through another anonymous survey. Right. Okay. What I would like to do now, is Christina still with us?
Yep,
She might
I'm
have
still
to-
here. I'm here.
Okay, great. I know you have to leave soon, but I don't know if you have any other.
No. I'm here for another hour.
Oh, okay. I got confused
Right.
in the time zone change. Great.
Yeah,
Okay.
yeah.
Okay. So I'll invite Christina and Mark to make any comments on anything they saw in the survey results, or any or anything else.
Yeah, just thanks for providing the feedback. And today we're going to have a little longer break between the lab activities and the core lectures that I'll be giving on magnetospheres and ionospheres. We'll be starting the lectures at 1 p.m. Eastern time or 11 a.m. Mountain time. So should have a little bit of extended office hour meal break.
Yeah. And how late do you want to run that till, Mark?
I'll push it about 15 minutes later than planned on the schedule.
Okay.
Yeah.
Great. Okay. All right. Good. Okay, so we're gonna switch over into the lab activity. And so give me a okay, great. Thank you. I just saw Tsigi posted the group 1 time zone group notes. So if you've got notes from your time zone group, feel free to post them in the Slack channel. Put up a, let's see, what are my choices? Put up a thumbs up if you were able to meet in your time zone group channel, and put up a like. I don't always want to use the surprise face. Let's switch over to let's see, what other choices do we have? You can oh, I see. Okay. Yeah, put up the like joy face if you weren't able to meet in your time zone group channel. So thumbs, I've seen a few thumbs up. Okay. Some joy. Okay. So it looks like about a 50-50 split. All right. So here's what I'd like to do. First, I'm going to take you through 1 or 2 features of part 1 that the intro in part 1 that I thought were important. But also what I'm going to do is I am going to send you back into your synchronous groups. And we can and when as part of the for the first part of your synchronous groups, you'll review some of part 1. Those of you who were able to look at it, you can show what you found out, and those of you who were able to not able to look at it, you can spend a little bit of time getting used to the interface and seeing how things should work. So we'll and then we'll try and do a quick wrap up before the top of the hour, and then send you into part 2 and see what you can discover in part 2. All right, so part 1. Let's see. So I'm going to share my screen again. I'm just going to do a 10-minute walkthrough. First off, so one of the things you should have noted is, so I sent you to this. I'm going to blow up make my font bigger so you can see it. I sent you this link here. So this particular run. So what we've done is we've got a series of runs that have been done under different conditions for for various features of the Earth's magnetic field and the solar wind conditions. And so the magnetic field in this case, so this. And one group or a couple of groups will explore this in part 2. The varying strengths of the magnetic field are here. I sent you to the double the dipole strength of the Earth's magnetic field to start with, just because it enhances some of the features that that you see. But the solar wind conditions for all these different cases were exactly the same. And if we go to that particular case, we can view those solar wind conditions, and these are given in these stack plots, which are very similar to some of the solar wind stack plots that you see before. Anybody notice anything funny about the solar wind conditions that we're using for this particular run? You can put it in chat, or you can. Okay, so somebody's got it. They're pretty constant, right? Over the course of, this is only a 2-hour run, so over the course of 2 hours, I've got exactly a density of 5 particles per cubic centimeter, which is a typical density of the solar wind. I've got exactly minus 400. So the direction of the solar wind is blowing out radially, or in the case of the coordinates that we're using XYZ coordinates, which are the geomagnetic coordinates. So it's flowing tailward. So away from the sun is negative, and so tailward at 400 kilometers per second away from the sun with no variation in Vy or Vz. And there's, I think this is the most strange portion of these solar wind conditions. Bx and By are 0 while Bz is negative. So this is for anybody who's got some experience in the solar wind. Bz being negative is, I won't say unusual, but it's certainly not. It's certainly an indication of some activity is going to happen, because it's now you're interacting with the Earth's magnetic field. The solar wind magnetic field and the Earth's magnetic field are against each other. Also, so if we go over to real-time data, then of course you see lots of fluctuations. So the order of the stack plot's a little bit different, but you can see that the solar wind density varies. It's above 10 here, and then it drops down to, I hesitate to measure that to take anything below 1 too seriously, but certainly it drops down to something that's below 10 and into the 5 region. Question? Okay, somebody's got a live mic, so if you've got a question, you can speak up. Although either Mark or Christina are monitoring the chat, I think. All right, so density, density does fluctuate between above 10 to close to 1 sometimes, and then fluctuates around 5-ish, between 5 and 10. Up here, you notice the magnetic field. The black is the total magnetic field strength, and so the red is just the Z component. Most of the time, the Z component is very small, right? 1 or 2 nanoteslas. Sometimes it fluctuates some, and then this is the angle, and you'll notice that the angle varies between about 135 and about 315, and that is telling you that it's about 45 degrees in the ecliptic plane, about 45 degrees, or 100, or exactly 180 in the other direction, relative to the Earth's direction, relative to the Sun-Earth line, that is. So it's either 45 degrees out or 45 degrees in towards the sun. So we're getting hit at some sort of an angle. So By and Bx should have some values in the component. So that Bz value here is very unusual. So the point of this all is these are idealized solar wind conditions that don't necessarily mimic real solar wind conditions, but it's a way to both exercise the model and explore what happens to the structure of the Earth's magnetic field under these various conditions. We've got one question in chat.
No, it's just pointing out that not only is the IMF-BZ normally pretty small, what's interesting is that it's the mean over weeks, excluding some transients, is 0. So it's
right.
One of the ways we calibrate magnetometers, the Z-axis, usually out of the spin plane.
All right. Let's see. All right. So that's one of the things I wanted to point out when you get to, I'm going to go back to here. When you get to this page, you should, so if you haven't gone through that, that's, you can skip over that portion of part one. When you get to this page, you should be able to click on view. Let me go back just to make sure I do that. View magnetosphere, and then click the update button, and pretty quickly, it says 55 seconds. It's usually faster than that. We can get to the visualization page. So these are, again, the visualization pages, the web visualization pages at the CCMC. So we're using some of their tools. And they have recently redesigned the page so that it's a little easier and cleaner to use. It's still a little bit clunky. I think they've upgraded, so where they're current in the current nomenclature, as we start to go into the cryptocurrency world and blockchains and decentralized sort of structures on the web. People were referring to that as Web 3. This, what Facebook and Instagram are thought to be Web 2 kind of tools. This is definitely a Web 1 tool. So not that that makes it bad, but it's just you might find it a little bit hard to navigate until you get used to it. So here's a XZ cut of a magnetosphere. And from this, and following through the instructions in part one, you should be able to explore some of the features of a magnetosphere and look for the bow shock, look for the magnetopause, look tailward, and see if you see anything interesting tailward. One of the cautions about this is I'm going to change the view. So for some of you, this should be a review. But if we change the view and I include the magnetic field lines in this, remember this is a 2D cut, and we're picking starting points for magnetics to draw magnetic field lines. And magnetic field lines are these constructions that happen, but they can happen in a 3D plane or a 3D volume. And so some of these, while there's no obvious ones here, but some of these you may see some unphysical situations or what appear to be unphysical situations. What you're really getting is a 3D field line that's being projected onto a 2D surface, and so you may be getting field lines appear to cross each other, and that's unphysical, right? But what it really is you've got multiple field lines that are in different planes that are being projected onto the 2D surface. So you may watch out for something like that. Okay. So for part one, if you haven't done some of this, you should skip to identifying the dayside features of the magnetosphere. Go to View Magnetosphere and start looking at some of those features. If nobody in your if you're in your time zone group, you find that one of you has or a few of you have gone through this, please share what you've discovered with those who haven't gone through it. Also, maybe show them how you made these plots. And then if you find that nobody in your time zone group has gone through any of this, get started on that. But you should also use the call the host button to ask for help so that I can jump in and help or push you along and support you in some of your explorations. So let me just check. Do you see that button in the breakout rooms, the call the host button when you go into the breakout rooms? Okay, Keaton gave me a thumbs up. Yeah, okay, a couple of people gave me a thumbs up. Yeah, so nobody's used it up until now, so don't be afraid to use that. Call me when you get lost. Sometimes when I write instructions, I don't always know what people are going to get stuck on. So And I don't want you getting too stuck on things. So we're going to take the next half an hour or so and explore what you've already discovered in your time zone groups, and then we'll do some kind of wrap up on that on part one, and then we'll go into part two. Okay, great.
Hey, sorry, Nick. Are we using our sync or the second version of the sync groups?
Yes, we will be using the second version of the sync groups, which I think Maggie will have handy to post in chat in case you've got to double check those.
Yes, I just posted it in the chat.
Great, thank you. And then I will have a third version of sync groups so that you get to talk to other people again for the next lab, for the next at the closer to the end of the week. Any other questions as to what we're doing next?
And I just wanted clarification. It's the sync group 2 that were just posted, not time zone. Yep.
Yes. Yeah, great. Yeah. All right. Okay, so if Maggie can open up the rooms, maybe she has already, we can go into those synchronous groups, and I will be around to check on people. And Mark, when are you here till?
I was just going to drop off in a few minutes.
Okay, great.
Yeah, so Nick, I'm here. Sorry, I have a bad, it's like I'm on my iPad, so it's sort of like,
okay.
Hi. Yeah, and I didn't realize it's normally when I connect on my iPad for a Zoom thing, it's like I'm just really listening and there's not really much. So now I'm like, wait a minute, where's buttons for breakout rooms? Where's annotation? You know, there's like, it's way more limited than I was expecting. And then I'm using my phone to try and like look at the Slack thing, and you know, this is a little more awkward than it is at home. But anyway.
Right.
So yeah, so sorry about that. Yeah, so I'm here for another 45 minutes.
Okay.
So
how comfortable or uncomfortable are you with the magnetosphere?
I'm pretty uncomfortable with the magnetosphere. I try and stay away from that stuff as much as possible. I just tell them what's coming, and then I go bye.
Nice. Okay.
Not my field. Yeah, I was actually just looking at the posted the lab they're supposed to be doing, and I'm like, okay, what do they need to do, and wondering how much of a help I'm going to be. So we'll see.
Well, part of the goal of part one is just to figure out, like, what am I looking? Which way is the sun?
Right.
Where are the buttons for figuring out which variable we should use, and what do these field lines look like? Why are there some green ones and some red ones? And so some of it's just introduction that is
right. So that part I could probably help with if people need help. But so they did this in their time zone groups, but now they're working in their synchronous groups, so they're supposed to share or something.
So some of them did this in their time zone groups.
That's right. You said it was only about 50-50, right? Yeah, I guess it was Sunday for a lot of people.
Sure.
Okay.
So for about half of the time zone groups, it was over the weekend, and they are just waking up now. But
okay.
Or well, they could have gotten up at 7. Like
I got up at 6:30. Come on, man. Okay. Do you want us to bounce around some of the groups and see how they're doing, or should we give them some more time?
Feel free. Nobody's yelled. So Maggie, if I mean, you'll probably get any like request for host, right?
Yeah, I should. I also made you a co-host, so hopefully it
Okay.
pops up for you as well.
I
But-
don't think it does. So, but
Okay.
you can like send me something on either find me in a room or send me something on Slack.
Okay. And are you gonna come back here, Nick, before you want me to close them?
I will come back and tell you to close when to close the rooms. Yes. So we'll be looking for it around 11.
11. Okay, 9 my time. 11 your
Sorry,
time.
9 your time.
You're
Yes.
totally no, you're totally fine.
I know the time zone. I'm like, constantly like, what? Wait, what time?
Yeah.
Yeah,
Yeah.
exactly.
Okay,
Okay.
that's great.
Okay.
all
Sounds
right.
like Nick's going to be a little bit on his own between I'm gone. Well, Nick and Maggie, you'll have Maggie.
Yes,
there'll be
wish
some
Nick
gap
the best of
between-
luck.
Okay.
Yeah, because I'm going to leave
think
and then I guess Mark won't come in for a little bit or something. Right.
Yes, right. So, all right.
So,
Well,
okay.
have fun
Sorry.
at TESS.
Yeah, thanks. We'll see how it goes.
There's an education panel with Sandlin Buxner on it, and Sarah Gibson and Sherilyn Morrow.
Yeah.
I wish I was watching, but I can't. So.
Yeah. Well,
all right.
Hopefully it'll go well. We'll see. All right. I can't actually see who's in which breakout rooms on this. I can just see that there are breakout rooms. Do you know where Mark went?
I think Mark left.
Oh, Mark just left. That's right. He had to leave. So, okay.
Well, I don't see the breakout rooms. Breakout rooms? Yes. Okay. Now I see the breakout rooms.
Yeah, Mark did leave
Okay. Great.
because he's not in any of them.
There's too many people in that synchronous group went on there. All right. Well, you know what? Oh, Dorcas is in twice. Never mind. Okay.
Yeah. I think she often joins twice because she's got, I don't know,
she's got
some audio thing or something.
Yes.
Yeah.
So I think she's got two devices. That works. So.
Okay.
I'm gonna join group 3.
You're going 3? Okay. I'll start with 1, I guess.
Okay. I just yeah. So great. And then I'll go to the end and work my way back.
Okay. All right. Sounds good.
All right, I was trying to do something clever and realized I couldn't, so I'm going to do something other clever in a different way. Nope, that's not it. Okay. So I'm going to cheat and talk to what Time Zone Group 1 did in their work, just to summarize some of the things that we did. First off, if you've got questions from part 1, put it in chat, and we'll see what questions what questions came up from part 1. So, all right, so these are some of the figures that you should have seen already. I think this is an interesting comparison. So on the left-hand side, oh, I see. This must have been modified from when you it got squashed. Okay, on the left-hand side is the sort of first initial phase that you see, and I'll talk a little bit more when we get to the line plots about what you should have seen in here. On the right-hand side, you've got the they plotted BZ here. Is it just BZ? Yeah, BZ. And how should BZ fall off with distance from Earth? Close into Earth, within a few Earth radii, how should it be falling off? What should be the relationship? Any ideas? If you were to plot BZ as a function of time of distance from Earth.
Which direction?
So what's you're going out radially from the Earth, and let's say you're within sort of 10 Earth radii. So if the magnetic field of the Earth is just a dipole, how should it be falling off? Yeah,
1 by r cube.
So 1 over r cubed, right? Just as a dipole. So it's when you plot BZ here, it's just going to be dominated by whatever's close to the Earth. All right, and you're going to get different directions, but very close to the Earth, it's going to be very large and it's going to fall off pretty quickly. So this would be again something that you'd have to like scale the same way we did it with the solar wind to see the variation that you wanted. All right, I'm going to scroll down. Aha. Let's zoom in on this. Oh, and I want to talk about a couple of things about this. Something I should have said offhand already. If you haven't explored this already, this simulation is an MHD simulation. And now I'm trying to remember. I think. Oh yes, this is the space weather modeling frameworks MHD code. I switch between that and I use the LFM Lions Fetter Mulberry code. And so, but this is the space weather modeling framework. So it's a full MHD code. It solves the MHD equations with in this case, with the Earth modeled as a dipole. You can vary the dipole strength and the dipole tilt. We've got a little bit of dipole tilt in here, as you can see. It's done on an adaptive grid, so that means that certain grid areas end up with more grid points, whereas other grid areas, say out here, end up with fewer grid points just because of the variation. So in the nose, you're going to get a lot of variation, so you're going to have a lot of grid points there, and in the out in the solar wind, you're not going to have as much variation, so you're not going to have as many grid points. the other thing in here is there's an inner boundary at about probably 3 Earth radii. That inner boundary, yep, thank you, Dorcas. I'll get to that in a minute. So that inner boundary is the field lines, and then the magnetosphere has to interact with a ionosphere model. In the case of this ionosphere model, I'd have to go look up what we used. I forgot what it was. You can use a wide variety of ionosphere models, anything from the simplest, dumbest conducting model that you can have, which is just a constant conduction with a Hall and so there's one conductivity that's perpendicular and one conductivity that's it's okay. Thank you, Pauline. So it is a constant conductance in the ionosphere, just to close the currents that are coming in. The state of the art today is to couple it with a more realistic model of the ionosphere that can vary, where the conductances can vary, where you get the interaction with the currents in the ionosphere, and you get feedback from that in terms of the ionosphere. For this, I just did the simplest model that we could. All right. Let's see. Dorcas was asking the black caps. These are supposed to be vectors, and they're vectors, I believe. Yes. So these vectors are the magnetic field vectors for this. So you can see that there's a strong change in the magnetic field. It starts based on the solar wind conditions that we fed in. So the solar wind conditions get fed in on the front side of this. So we've got plasma being fed in with the constant density and constant velocity and constant magnetic field going towards the Earth at -5 nanotesla. But then here you can see that it switches from being solar wind magnetic field dominating to right at the nose here, right at the magnetopause, it'll switch to the magnetic field of the Earth dominating, and so it'll go from negative to positive. Great. And I'm gonna, I'll take a look at this nose in more detail in a couple of minutes. I just wanna, here's this plot that I wanted to get at. So kind of summarizing some things, I'll put in a complaint to the CCMC. They changed these plots, and I don't know why this color here and this color here are so close to each other. If you look carefully, I think this is a quote-unquote blue. It's not a very good blue, though. It's pretty black to me, and this is black too. So, but from context, we can tell some of the differences that are going on here. So you'll notice here that we've got a density that's pretty small in the solar wind. Although, oh, I see. Hang on. I'm mixing up. So this is where the color gets in the way, right? So I know that we put in a 5 particle per cubic centimeter solar wind. So this must be the density line that comes in here, and then it hits the bow shock, and suddenly the density increases. And you can also see that the velocity is going, it's a pretty high negative velocity going from -400 and then jumping up till ultimately hitting 0 here at the magnetopause. So when you get a sharp change in the velocity, and you're going to get, when the velocity is going way down, you're going to get pile up in the density, and you're also going to get some pile up in the magnetic field. All right. So some people noticed, they zoomed in. One group zoomed in on this region right in here, and noticed that there was an increase in the magnetic field from the 5 nanotesla to some plus 20 nanotesla as it increased, and then it dropped back down again. And then notice that that then takes on a 1 over r cubed plot. If you were to plot 1 over r cubed, that would probably fit this portion pretty well. Questions on anything I said so far? You can put it either in chat or just unmute yourself. Last thing I wanted to point out, I asked somebody to put this in, yeah, great, this image here that we're gonna try and expand. Can I expand that? Nope, it doesn't want to expand. So,
I have a question about the last figure.
yep, please.
The peak of the dynasty, I think.
Yep.
Yes, I can understand these variation with the velocity of the solar wind.
You can or cannot?
I can't.
Okay, so first I'm gonna turn off my air conditioner so I'm not yelling over it. So the peak in the density is happening because so the solar wind velocity is coming in at 400 kilometers per second. The solar wind is heading the magnetopause. A lot of it's getting deflected around the magnetosphere, but that doesn't get deflected. That density starts to pile up. That plasma starts to pile up, right? Because suddenly you're hitting a traffic jam, right? And so the velocity so this is the definition of a shock, right? The velocity changes rapidly, and that's the definition of a shock. But then when the velocity changes rapidly in this particular type of shock, the density is going to increase because you're just going to get, it's like traffic. It's just piling up there as it slows down.
Yes, and then it stable for a while and then decrease. So how density decrease while the solar wind increase and go through the magnetosphere?
So I would not say the solar wind goes through the magnetosphere. I would say that the solar wind actually piles up in this area called the magnetosheath and doesn't penetrate normally into the magnetosphere.
Okay, yes, it's
Okay.
clear.
So the only place it can penetrate into the magnetosphere is it can come in through these open field lines that go into the polar cap.
Mm-hmm.
Okay. But it can't penetrate through these closed field lines.
Yes, it's clear. And according to the magnetic field magnitude, it still decreases and then increase after the phase recovery phase. That's right.
Well, I would not refer to this as a recovery phase. This is a static.
According to magnetic field fluxes, yes, the green one.
Right. So it's decreasing as a dipole here, and then you get the interaction in the nose, in the plasma, in the magnetosphere, in the magnetosheath rather. And so you're going to have some interaction. You're going to get piling up in the magnetic field there.
Okay, thank you.
Okay. All right. One more thing I just wanted to share here, and then we'll take a break and see how far we can get on part 2. That did, all right, so the one thing I wanted to show here is somebody was asking me about can we see reconnection in the nose? And we can, if you zoom in, you have to use the plot area to zoom into a particular region. And you can see that field line right there, and you can start to imagine other field lines that are nearby it. I'll draw that as best I can, right? And then their companions doing something like that. And you'll notice that so you're starting to get an X point somewhere around here. Notice that the value of BZ, or the direction of BZ, is negative here, and then it's positive here. So somewhere in here, right, there's got to be an X point where you get a null point, where you get zero magnetic field, and you get a reconnection right there. So you're going to get reconnection going on here when BZ is southward. Remember, this is an idealized case with a constant BZ south for a very long period of time, and you're not seeing any of the fluctuations. All right. Any other questions about part one? All right, let's take a 5-minute bio break, and then I'll give you some instructions. So let's be back by 11:30, or in about 7 minutes, or 6 minutes, I guess. So 11:30, or the top of the hour. So the bottom of the hour for most of us, and the top of the hour for those on the half-hour time zones. Right? And I'll give you some instructions then. Okay, I'm seeing about, I don't know, about 3/4 of the people back. So okay, all right, a couple of more people are coming in. Oh, Muhammad is re-logging in. Great, welcome back. All right. So, let me find I gotta find what I'm looking for. Don't want to do that, come on. Oh, this is why in TV I have people assigned to this. All right, here we go. All right. So, part one was warm up for part two. And so there were at least two groups that went on to that started going on to part two. So if you started going on to part two, like put your group number in chat so I can see what you were doing, because I want to assign different portions of part two to different groups. Yep, group one started section one. There was at least one other group that started section one, exploring different dipole strengths. All right, nobody wants to fess up to that. Group 5 started section 1. Great. All right. So, groups 1 and 5, you will continue doing section 1. And groups, so we're going to do, there's 4 sections, so we're going to do this in modulo 4, right? So, groups 1, 2, 3, and 4 will do well, so groups 1, 2, 3, and 4 will do the section that is their number, right? So group 1 will do part 1, or sorry, question 1, variation on the standoff distance in the dipole string in part 2. Group 2 will do different dipole tilts. Group 3 will do magnetospheres in different locations, and group 4 will do dipole reversal. 5, 6, 7, 8 will subtract off 4, and so group 5 will do again number 1 in part 2. Group 6 will do 2. Group 7, 3, and group 8 will do activity 4. Is it clear which groups are doing which? Getting a couple of thumbs up. More thumbs up. Great. Okay. Great. So we're going to go back into your breakout rooms, and we'll finish up this exercise. I will check in. Well, I'll be checking in with everybody, but we'll try and aim for wrapping this portion up at 12. But we'll see how we are doing. Mohammed, do you remember which breakout room you were in? Oh, he's gone. All right. Just us.
Very good.
Okay, great. All right, I'm gonna go check on something, and then
Okay.
So can somebody from group 2 share theirs? If not, we'll go to group 6. All right, is somebody from group 6 ready to share? I don't have the groups up, so I don't remember who's there. So
Well, I'm from group 2.
Yeah,
We
great.
could not, we could not finish all the questions that were given there. But I guess one of my group mates have this document which we can still share.
So
So
share
Matthew,
one. Share.
if you
Just show us one thing. Is all I'm
yes, of
asking.
course, but I do not have this document. Matthew has it locally. So
yeah, no, I can share one. Give me 1 sec.
Yep.
Yeah. It's on the Google Doc. I'm just gonna share it. Can you guys see the screen?
Brilliant. Yes.
Yes, so I guess we've only managed to do the qualitative part. We haven't managed to do the table of results
great.
yet. Yeah, I guess for qualitative, the dipole tilt changes where the reconnection X point is. It seems that as you tilt from 11 degrees towards 90 degrees, the reconnection X point on the day side goes to a higher negative latitude. And when we zoom into the night side as well, we find that we're getting less and less closed field lines in the midnight sector, but we still see a high latitude reconnection on the night side.
Yeah, can you zoom in on that a little bit? Great, yeah. Group 6, you got anything to add?
I think, I'm not sure actually, but by changing the dipole, the magnetosphere shape will be changed as well, and it will affect on the position of the reconnection point of the magnetosphere, or there are many consequences will be changed.
Yeah. So, and one of the real life, so this isn't just playing, right? Because there are real life applications to this. Neptune and Uranus have significant tilts relative to their spin axis. Their magnetic field is tilted relative to their spin axis. And I'm not sure how much it's tilted relative to, say, the equatorial plane, but it could be a significant tilt relative to the equatorial plane on this too. Great. All right. Thank you for sharing that. We'll move on to 7, group 7. You got something you can show us?
Yes. Can you see the screen?
Great.
Yeah, so we wanted to identify the position of the X point on the day side. First, we tried to use either the magnetic field, the velocity, or the density. We confirmed what we saw before about the Z component, that it roughly scales as 1/r cubed, close to the Earth. But when we zoomed in, we couldn't find like a clear indication where the X point is. But as the other group showed, this might have to do with the tilt. So we went again to the full 2D maps, where we can observe clearly a reversal in the polarity of the Z component. And we found that this happens close to 14 Earth radii. And then we moved.
And that's for which distance from the sun?
We didn't calculate that. So
okay. This is that is so. Which case were you doing?
Well, the same as the other group showed for the tilt. So
okay.
And then we try to make an estimate about the size of the current seat on the night side. Well, here you have a little bit of freedom, depending on how strict you want to are. We would say that it is around 40th radii word, based on the velocity, but again, you need to change all the other parameters, possibly with the magnetic field also.
Okay, great. And what's the corresponding group 3?
Yeah, Nick, this is Shovik. I have a specific comment that if you really want to identify the X point, I think the current density is a better variable to plot with, because in the reconnection region, you must see a high current. So though we don't have any picture with us, but we have plotted the current density for finding the X points in the day side. And we have seen a significant increase in the current density, which basically signifies for the X point.
Okay. And so, yeah, so that's a good point. I think we're starting to get to resolutions in the simulations where the current density is well defined, or it's well confined rather, for the plasma sheet. But it's not always depending on the resolution of the simulation, it's not always well confined, right? So sometimes you look at the field lines. Great. Group 4, something you want to share?
Yeah, sure, I can go. So we looked at changing strength of north-south dipole. And I'll share my screen. And what we have here is on the right, we have a stronger G10 of about 0.95. Then this is decreasing. We noticed a slight compression in the nose up here. And then when we have a negative G10, so a negative north-south dipole, it basically, we sum up, it becomes a mess. We didn't have much time to look over it much.
Right. So can you zoom in on that for us? It's I think it, yep. Okay. A little bit better. I think go to the zoom on the top left there. Yeah. Nope. Where it says 100%.
Thank you. Thank you.
Great. Yep. And let's look at the yep. Okay, great. So yeah, it is a little bit hard to discern, but you've got closed field lines in all sorts of different places and open field lines crossing the closed field lines. So there's 3D field lines being compressed onto the 2D surface. And where do you think there might be good aurora in this?
How to describe it? You can see my screen. Yeah, right around in these locations right here.
Yeah, probably. Yeah. So weird places for aurora.
Yeah.
And so I think you might have aurora all over the place. And the other group I think was maybe can make a comment on Mars and the weak field. So this is a situation where the Earth's dipole field is reversing. And so you go from a dipole field to toroidal field. So you're losing the dipole component, but you're getting the higher order components are become important, but they aren't as strong and they drop off more quickly, right? All right. Does the other group have a comment on Mars?
I can chime in since I study Martian aurora. So one of the things that we were noticing was that when you reduce the dipole to being almost non-existent, so like really small fraction of the current percentage, then we started to see those green areas that Nicholas was just showing kind of everywhere on the planet. And I was just commenting that that is definitely in line with what we see on Mars, where we see proton day side aurora across the entire day side of Mars, and then another kind of diffuse aurora across the entire night side of Mars. And it's not constrained to the poles or any specific region. It does get a little more funky with Mars because you have some remnant crustal fields. And there are another type of aurora that are confined specifically to those. But yeah, it was interesting to play around with the model and see, I guess, a visual explanation for what we observe on Mars.
Great. Okay, so with that, I'm sorry that the wrap up took, or that we used up more some of the extra break that we got, but I thought it was helpful to get everybody to wrap up what they saw. So. Let's take a break for a half an hour and we'll come back for Mark's talk at 1.
And Meg, thanks. So see if you can put a stamp next to awesome. And since for your grading, you get 1,000,000 points for every stamp you put down. So this is the opposite of Nick's. None of the. This is all of the above. So the main punchline for this lecture is magnetic fields are really key for everything. Let's see if I can clear all drawings. Okay, thanks. Oh, we're gonna try to move forward. Where did my mouse go? And I should have taken this to heart that whenever we do this, we get.
You have to close the annotate window.
I know, and it's not even giving me my mouse.
Oh,
So, yeah. So I will get there. But two zeroth order things to remember. One is that magnetic fields are super important. And so what do you think the most important instrument that there should be on every heliophysics mission? We're going to get there. Let me pause my share. Boy, I can't even. Okay, I can kind of get there. Boy, this is terrible. Okay, so we got one right answer. Those are worth 2 million points each. Haha. And so, of course, magnetometers are the most important. So one of the things that I tried to discuss in all of my classes, even graduate classes, is some metacognition skills, essentially how to learn. And one of the weirdest things that I've is an eternal frustration is that all my career I'm working with students, and students that are often very experienced students. So they're not only have gone through 13 years of primary and secondary education, they've gone through 4+ years of undergraduate and often many years of grad school, but they hadn't taken the time to actually dive into the literature on learning. And there are School of Educations and psychology and cognitive studies researchers that actually try to understand how people learn. And so if you haven't dove into those sort of study skills, but really it's more of the research, I urge you to do that. And one of the things that helps me, and I know helps a lot of people learn, is to be very intentional on how you participate in things like the Heliophysics Summer School. Essentially, we're going to have 2 weeks worth of lectures on all different types of topics, a lot of different activities. You're going to be developing new skills, learning new concepts, new vocabulary, new regions that's not in your wheelhouse. How do you learn? How do you keep track of everything? If I said, take out a piece of paper, we're having a quiz on last Tuesday's lectures, it's like, how would you even remember what we did last Tuesday? So a conceptual framework is a systemic way of organizing the information that you hear. And one of the things you should do is assess to see if you know that information already. If you don't know that new information, try to understand where it fits into your existing information, because all of us know a lot of different things. We have different experiences. And when you learn something new, that's one of the first things to do is try to figure out where it fits. Is that a physics concept? Is that a conservation of energy concept? Is it a region concept? And so in terms of heliophysics, magnetic fields are important pretty much everywhere. So what are magnetic fields? How would you describe a magnetic field? And they're essentially force fields, energy fields. They're part of electromagnetic radiation, which is one of the dominant means of energy transfer in the universe, but they also are part of alphanic or magnetohydrodynamic fluctuations. They control the propagation of plasma waves as well as the MHD waves and light. They define particle motions, boundaries, and when you start thinking about plasma parameters. One of the terms we've heard already is plasma beta, NKT over B squared over 2 mu naught, essentially the gas pressure, ideal gas pressure, compared to the magnetic pressure. So magnetic fields contain pressure as well. So you'll see this all over the place. How do you know you crossed the magnetopause? What's the boundary of the heliosphere and the interstellar medium? A magnetometer can help you figure that out. And so we live on a magnetic planet in a magnetized heliosphere in a magnetic universe. And if you're wanting to work with magnetic fields, take a look at my webpage, and always looking for postdocs. And this is my license plate for my car. So not only a Star Wars, Star Trek, but also X-Men fan. So in one of the first Heliophysics Summer Schools, gave a lecture and wrote a chapter in one of the heliophysics textbooks. It were posited that there are essentially 3 fundamental magnetic structures. So part of this conceptual framework, part of being a physicist, is trying to unify things, trying to simplify things, trying to classify things, find similarities between things. And so for magnetic fields, one of the interesting aspects is that there's essentially 3 fundamental magnetic structures in the entire plasma universe, and called these cavities, or essentially where a magnetic field carves out its region in space, or magnetospheres, or heliospheres, or astrospheres. Current sheets, wherever you have shear in a magnetic field, so the magnetic fields are in opposite direction. They don't have to be anti-parallel. They just have to have some angle. You're going to set up a current sheet. And that's one of the Ampere's law, the curl B equals mu naught J. Essentially, if you have a curl of a magnetic field or a shear of the magnetic field, you need to have a current. And sort of the quanta of magnetic fields are the flux tubes. So essentially, in a magnetized plasma, that plasma is going to feel a Lorentz force and be trapped on that magnetic field line. So essentially that magnetized plasma defines this volume, or this tube that can be threaded through the entire heliosphere. And so thinking about magnetic fields from eruptive processes on the sun, or features on the sun, like flux ropes or filaments, or all of the planets, we can start thinking about these fundamental structures. So one of the other interesting aspects, universalities, are these cavities. So this is the Heliophysics Summer School, and we essentially study everything inside the heliosphere. And so going back to that Greek idea of spheres, nested spheres, or Russian nesting dolls, you can also think about that every magnetosphere is the same. It has essentially the same shape. It must be embedded in some type of other magnetized plasma, and so that defines its shape and size. And it also could have an intrinsic or induced or remnant magnetic field. But essentially it looks the same, often a dipolar structure inside with a stretched, depending on the direction of the outside flow, into a long magnetotail. And this diagram shows the smallest magnetosphere of the planets, Mercury, and how it would fit inside the Earth's magnetosphere. It's essentially the size of the Earth. And then, of course, the Earth entire magnetosphere can fit inside of Jupiter, and Jupiter's magnetosphere can fit inside of the dipolar region of the Jovian magnetosphere. But of course, inside the Jovian magnetosphere. We know that there are other magnetospheres. Ganymede has its own intrinsic magnetic field. So a moon has a magnetosphere. And so instead of a solar wind propagating by it to define it, it's essentially the rotation velocity of Jupiter going over the moon that defines that velocity, that structure. And of course, the Jovian magnetosphere, as all these other magnetospheres, are embedded in the magnetosphere of the sun, which we call the heliosphere. And so you can look at Hubble Space Telescope and now James Webb Space Telescope images of stars, and you often see these teardropped astrospheres where the solar or stellar winds from one star are interacting with the interstellar medium, setting up boundaries and shock waves. So this is a universal part of heliophysics and astrophysics, is that things are magnetized and set up fundamental structures. And so last week took a look at the sun and the mechanisms that convert that magnetic energy into particle kinetic energy and photons. And you can see how dynamic it is in this SDO-AIA image. But when you look at the sun in this wavelength, the structure that really comes out at you are these loops and these rays. And these are defined by the magnetic field on the sun. And you can see that there's active regions, these bright spots where there's a lot of energy coming from the sun. They're crackling with the magnetic field. And so that convective cycle of the granules and supergranulation and around the sunspots move those magnetic fields. So you get this twisted and tangled magnetic field. And if you calculate how much energy density there is in the photospheric field, it's way more than you need to set off a flare. You know, the conversion rates just need to be a percent or so of the available energy. I think Mark Chung explained it that you know, there's enough food for everybody on Earth, but we still have starving people. It's not that you have to find the energy. The energy is there. You just have to be able to convert it. And so that's part of this magnetized heliosphere. Where does all the structure and dynamics of the heliosphere come from? It comes from converting magnetic energy into particle kinetic energy and photons. So going back down to the surface of the sun all the way to the Earth, where does the aurora get its energy? Where do geomagnetic storms get their energy? It's from the conversion of magnetic energy into particle kinetic energy. And so what's the most important parameter of heliospheres? Follow the money, follow the energy, and that's in the magnetic fields. So one of the most important equations, or probably the most important equation when you're thinking about the creation and destruction or the evolution of magnetic energy, is this bottom one. This B squared over 2 mu naught, that's essentially the energy density of a magnetic field. So you see that it's proportional to B squared, so the magnetic field squared. So if you look at the photosphere of the sun, you know how many Gauss that is, or how many microteslas or milliteslas, and then you square it. So there's a lot of energy density in the magnetic field. But where does it come from? So how do I change a magnetic field? This induction equation, which you've seen a couple of times already, it is where we'll spend the most of the time today. But it essentially has two terms. It has this term here that's a del squared B. Can anybody type, whenever you see that type of equation, what's the name of that equation? Or what does it signify or represent in nature? this Laplacian. So think of the process and not a distribution. Diffusion, awesome. 5 million points. So whenever you see that this differential equation, that you have this Laplacian as a function of a time derivative, that's telling you diffusion. So heat diffusion, or if you open up a perfume bottle, how long does it take for the smell to fill the room? Joe Giacalone talked about the solar energetic particles being fired on a very narrow field line. But there is some diffusion, some particle diffusion, even though they're trapped. There are processes to allow those gyro orbits to pop onto other flux tubes. And so this diffusion process is a universal process, and there's often a coefficient out front that gives you information about some of the time scale of that process. So in this case, this diffusivity talks about the diffusion of the magnetic field. So this is essentially a way to get rid of the magnetic field. And that time scale depends on eta. So eta could be such that it happens really quickly, or it could be really slow. And so trying to understand that property of a magnetized plasma or a astrophysical body is part of trying to understand the origin and evolution of a magnetic field. So when we talk about remnant magnetic fields, those remnant magnetic fields like on the moon and Mars, it's because the diffusivity of the magnetic field in the rocks or in the crust of the planet is slow. And so there's still some remaining even after a billion years or so, whenever the dynamo turned off. Sort of the source of this plasma is this transport equation, this curl of U cross B. What is another symbol for U cross B that we've already heard about? Go ahead and type it in the chat. Velocity, yeah, awesome. 5 million points for Pauline. The electric field, right? So that's this other relationship. So essentially we have this curl of E or U cross B. And so this electric field, this motion of the magnetic field can generate, self-generate a magnetic field itself. If the diffusion coefficient is really fast, we can get reconnection. So we've heard about reconnection quite a bit already in solar flares and coronal mass ejections. Magnetic reconnection is also a fundamental process in all the magnetospheres on the day side magnetopause of the Earth. If the IMF has a southward component, we can have magnetic reconnection, and that flux, open flux, can be converted or convected to the magnetotail, where you can get reconnection in the magnetotail or reconnection. And then this Dungy cycle, or this convective cycle of magnetic flux, can cycle through. But one of the interesting aspects of magnetic reconnection is it not only changes the topology of the field, it essentially connects two field lines together to make two new field lines. It can take an IMF field line and a closed, or a field line connected both ends to the Earth, and make two new field lines that are open. One end is connected to the Earth, and the other end goes out into the interplanetary magnetic field. But also, it can take some of that energy, that B squared over 2 mu naught, and convert it into particle kinetic energy and motion. So when you think about why are things so dynamic and moving around, if you can liberate that magnetic energy, you can have flux tubes, magnetic tension, snap things like rubber bands. So I like to think of flux tubes, and particularly the solar wind, as this convecting bits of rubber tubes. So they can get twisted up, and so you can get kink instabilities with these flux ropes that we heard about with Antonia's modeling. And then sometimes we can actually cut those or reconnect those field lines, and they will snap back with that magnetic tension, leading to a lot of dynamic processes. So when you think about why do we have magnetospheres, it's essentially because everything's magnetic. So magnetic field, you can think about the energy density in it, the magnetic flux and the flux tube. You can think about it as field lines that help exert a Lorentz force on charged particles. There's this J cross B or magnetic tension. And all of these give rise, balancing with the plasma dynamics, the pressure gradients in plasmas or collisions or viscosities or the other plasma, rho v squared, ram pressures. Coupling all of those in your momentum equation give rise to explain all of the structure and dynamics of the heliosphere. So this is a computer simulation of the Earth's internal dynamo, geodynamo, that was developed by colleagues at Los Alamos, Glassmeyer. And essentially a dynamo for a geodynamo, magnetic dynamo, or solar dynamo is essentially a self-sustaining magnetic field. And you go, hey, a magnetic field has energy. How do I create this energy field? So the conservation of energy says I need to have energy from somewhere else. And so that somewhere else is essentially plasma motion, charged particle motion. And you go, well, where do I get that charged particle motion? And for planets and the sun, it's the rotation that gives rise to, as well as thermal gradients that give rise to convection, can set up fields that essentially can build on each other and be relatively stable. We know that the Earth's magnetic field flips every 600,000 years or so, and the sun's magnetic field flips every solar cycle. And so there's dynamics in the dynamo that we still are trying to understand what those actually sets those key timescales. But we know it's the fluid, the plasma dynamics of these charged particles through rotation and convection that give rise to the dynamo. So these MHD equations, we've seen pretty much every lecture. The top equation is the continuity equation, essentially for this simplified aspect for the magnetosphere, essentially that the only way I can change the density of my plasma, and it could be number density or mass density, is to move it in or out of my volume. What we'll talk about in a few minutes is ionospheres, and that right-hand side is no longer zero. There's source and loss of ionized plasma that we have to worry about. This d rho v dt is essentially the momentum equation that we've seen over and over again. Newton's second law, F equals ma, F equals m dv dt. And in this case, the m is multiplied by n, so you can think of that as rho. And in this case, we have plasma pressure terms, electric and magnetic fields. And this J cross B, we can rewrite that, and you've seen it expanded in a couple of slides, that using Ampere's law, this curl B equals mu naught J, we can write this as the curl of B's in Maxwell's equations. So what are the fundamental plasma physics and plasma parameters? Mass density, composition, because of course that N could have a subscript. It could be Ni or Ne, or depending on the planet, could be CO2 or it could be N2O2. So they could have very different species. We also need to know about how things move, that dV/dt, and how the velocities change. So we need to measure that. The temperatures, densities, magnetic fields. And what's interesting about the magnetic field, those B's and E's, there's essentially different domains depending on the temporal scale. We have the very high frequency electromagnetic radiation that are essentially pure energy photons moving through the system. And so radiation is one of the dominant forms of energy transfer in the heliosphere. But in some locations, that radiative energy is more important, like at the sun, where you have this conversion of magnetic energy not only into particle motion, but you could actually heat it and give rise to radiative processes as those particles accelerate or decelerate, or actually heating the gas, just having a black body glow. Some of that energy can go out as photons. But when you start thinking of longer time scale or longer spatial scales, or shorter, or sorry, when you're thinking about longer time scales and bigger spatial scales, these B's and E's become more DC, more ultra low frequency, and they take a life of their own. And that's one, Hannes Alfvén, the Nobel Prize in Physics, essentially discovered something that Maxwell overlooked. And when Alfvén attempted to publish his papers at first, they were rejected because Maxwell would have thought of it. But you can think about these slower waves that are a combination of an electromagnetic wave and an acoustic wave, or a sound wave. So these magnetoacoustic waves or magnetohydrodynamic waves can give rise to energy flowing through magnetized plasma. And so it is a fundamental part of heliophysics. So you've seen all of these equations last week, and you can't have a lecture without a comic. And so I assume most people have seen this over and over again, but if you haven't seen it, XKCD is a great sort of PhD student. It's sort of like the Lego grad student, has comics that are geared just for us. And this is also, we talked about the Upcomer 5 AGU session. And so if you have never attended one of those, I highly recommend attending one, because it takes a lot of work to simplify the work that you're doing in language that everybody understands. And so if you say the word MHD to non-Heliophysics Summer School participants, you're probably going to lose somebody. So go ahead and type in the chat. Where do magnetic fields come from? Let's see if this is what I wanted to do. Yeah. Where do magnetic fields come from? And you can just do a bullet point: moving charged particles and plasmas. Yep. So that's one place. Dynamos, core of the Earth. Anybody have a magnetic field near them? So yeah, Earth core. So if you have a laptop that has a magnetic latch, or if you have a magnet holding up paper up against your bulletin board, you essentially have this lodestone. You can make electromagnetic magnets. Essentially, any current will create a magnetic field. Your Biot-Savart law. Faraday essentially invented the generator and the electromagnets. So they come from moving charge, and you can get that in a current. You can get that at the atomic level. So essentially thinking of a Bohr model of an atom, you have an electron moving around, so that has some dipole moment, some current element. And so if you can get in a material all those little domains lined up, you can get a permanent magnet. So magnets are all over the place, and all you essentially need is matter. And if you can get it to move, the better. Your laptop inside your little earbud, so you have a little magnet in your ear, essentially a speaker cone. So we use those all over the place. Okay, so for the Earth's magnetic field, where does the Earth's magnetic field come? And so there's an entire sub-discipline of geophysics that essentially takes your magnetohydrodynamic equations and tries to set up a self-sustaining magnetic field. And so for the Earth, the geophysicists have, using seismology, have identified that the Earth has a iron core and a molten iron outer core. We're spinning. We have differential heat between the inner core due to the high pressures. And so we can get convection inside the outer core and the mantle. And so this motion can set up essentially current loops that can be aligned, that can set up the global magnetic field. So for all of the planets, Mercury, Earth, Jupiter, Saturn, Uranus, and Neptune, and the Sun, we have some type of molten or ionized fluid that's moving around due to the spin of the body. And then couple that with some type of thermal convection like we have in the Sun, we get this motion in these outer layers that can move this conducting fluid. So the hot fluid rises, cold fluid sinks, and you start getting these current loops. And so if you can set up those current loops in such a way that they can all mutually add to each other, you can create a magnetic field. And so, hey, this magnetic induction equation again, this is the most important equation for dynamo theory. So if you're doing the Sun or a planet, you'll be looking at this again, this diffusion term, essentially at this rate of decay due to dissipation, and this curl of E term, this magnetic, you can think of it as a buildup or breakdown, this transport, this motion will define your dynamo, will define your planet if you have a permanent dB/dt. So one of the things that plasma physicists, geophysicists like to do is make dimensionless numbers. So beta is a dimensionless number that essentially is the ratio of plasma pressure to magnetic pressure. So just by knowing if beta is greater than 1 or less than 1, you know which terms are important in your momentum equation. Is the plasma pressure terms important, or is it the magnetic pressure terms that are important? And so if you remember from all of the previous lectures, we had this big, long momentum equation. And for the most part, I'm thinking of Antonia's, we set all of them to 0. And Sue Leprey's talk, gravity is not important and collisions aren't important and the magnetic tension. So how do you justify setting these things to 0? You essentially have to look at the magnitude of them compared to all of the other quantities. So essentially comparing any quantity in a single equation to another, you can make a dimensionless number. And so looking back at your induction equation, since it only has two terms, this dimensionless number, this sort of transport or breaking or making term to diffusion term is called the magnetic Reynolds number. And so if you have a magnetic Reynolds number greater than 1, your creation term is bigger than your destruction term, your diffusion term. And so the other thing that we like to do in physics is once we have an equation like this, we have this del operator that's essentially a spatial gradient. We know that that's something proportional to lengths. So we can get all of our L's together and then cancel those out. And so essentially what we have left is essentially a velocity and a scale size, or characteristic scale size. And so depending on what that is compared to your diffusivity, you can have a dynamo action or not. So essentially things that are moving fast over big length scales are more likely to give a dynamo, or conversely, you can get a really low diffusivity, but you're essentially looking at this ratio. So to finish up, I'm just going to touch real quickly on the sun. Imagine that the solar dynamo is very similar to the Earth's dynamo, except for we don't have this crusty thing and solid, but essentially we have rotation and convection going on the sun. Differential rotation adds a interesting aspect of it, is that if you are able to set up a small magnetic field that has this meridional aspect of it, you're going to make an azimuthal component just because the difference in velocities, this guy is going to stretch that out. And so you can start looking at your equations. Imagine that we have an induction equation, and we can look at the magnetic field and components, azimuthal and meridional, and we can look at the velocity, azimuthal and meridional, or toroidal or poloidal is another way of saying the same thing. Essentially, you can plug those representations of B in component form and solve. And essentially, you're going to get a induction equation that will generate a magnetic field. So this is the alpha omega dynamo. So essentially, taking your equations of motion, taking your induction equation, throwing in some assumed relationship between your azimuthal electric and magnetic fields, or this creation of energy, or U cross B, and you can get a self-sustaining dynamo. Okay, so we talked about this. Essentially, you can get magnetic fields everywhere. A lodestone, a magnet has its name. Lodestones were first found in a part of Turkey called Magnesia. So that's why we call them magnets. But we can now make electromagnets, as well as think about the fundamental atomic scale condensed matter physics of a permanent magnet. Then, of course, Maxwell's equation tells us a dE dt gives rise to a magnetic field as well. So just to summarize, magnetized plasmas is heliophysics. And then if you're going to start thinking about this magnetized heliophysics, there's sort of three fundamental universal structures that we find everywhere on the sun, in the planets, in interplanetary space, and presumably throughout the galaxy and even intergalactic medium. These flux tubes, current sheets, and cavities. Okay, so I'm going to open it up for discussion and questions.
There did not appear to be any questions. Oh,
Pratik, go ahead and unmute yourself if you have a question.
Yeah, am I audible?
Yes, you are.
Yeah. Thanks, Art. So, can you please tell me that what would be a good way to define the characteristic length of a system? So it's the one thing that I almost every time get very confused.
Yeah, and it's actually not as easy as you would think. And a lot of the early controversies, like the Sweet-Parker-Petchek reconnection model, they assumed one scale size going across the current sheet, and the diffusivity was much too small to get explosive reconnection. But one of the things that you should always fall back on too, if you're trying to either look at data or develop your model, is theory. You can sort of think of a hierarchy of scales. So can anybody either unmute or type, or maybe even you, Pratik, what would be one of the smallest fundamental scale sizes that have that's proportional to B? And I waited 8 seconds. All right, we got it. You're right, both of you. So essentially the gyro radii, or the Larmor radii, named after Larmor. Anybody know what that equation or of either the time scale or length scale? What is it proportional to? You don't need the. So for the gyro radii, usually it's your QB over M is essentially that time scale. So the charge, so an electron or proton has a Q of 1, the charge of an electron. The M is the mass, and B. And so the other thing, if you're actually trying to calculate a scale, could be that perpendicular component of the velocity to the magnetic field. But essentially, the bigger the B, the faster you're going, right? And so what's bigger for the same energy, an electron or ion Larmor radii?
so Mark, while people are answering, are those two different names for the same thing?
Yep, Larmor radius and gyro radius are the same. And cyclotron frequency or gyro frequency is used interchangeably. Yep, so if you think about the ion's going to have a larger gyro radius. So one of the smallest fundamental scale sizes of a magnetized plasma are energetic electron Larmor radii. And so MMS, magnetospheric multi-scale mission, was a $1.2 billion NASA mission, which is trying to answer the question of what is the physics responsible for reconnection. And it turns out it's approaching the electron gyro radii. And so they needed to have spacecraft really close together, measuring really fast timescales, because they have to measure these electron timescales at electron spatial scales. So Cluster was measuring more of ion scale size. And so when you think of a flux tube, a characteristic length scale of a flux tube would be on the order of an ion gyroradii. For reconnection, you would be thinking about the diffusion region, the region that has the largest eta, and that turns out to be on that electron scale. For dynamos, we often think of the scale size of a convective cell. So if you think about the Earth, there's actually these little cylinders that get set up, but the size of the body will have some constraint on the scale size of that convective cell. So for the sun, it's essentially from the photosphere down to the tachocline, or down to the boundary between the convective zone and the radiative zone. And so that's some fraction of a solar radii. So those are usually what you do when you're trying to figure out a length scale, is trying to figure out some physical or theoretical possible length scales. But then you can argue on if it's a full convective cell length, or is it a half length, or even smaller.
So Mark, maybe we can take
Yep.
a 5-minute bio break.
Awesome.
Okay, and then, and of course, Mark will be around for office hours afterwards.
Yep.
So
Great. So there's a couple of things. I started late because I was just on a qualifying exam for a PhD, and if you ask me to be on your qualifying exam, I almost always ask one question first. Tell me the time and length scales of your problem, because that really gets to the heart of physics. And you can tell what type of physicist you're talking to by what type of units of length scale they keep in their head. If they talk in nanometers, they're a spectroscopist, right? If they talk in AU, they're a planetary person, right? So a megaparsec, they're a cosmologist, right? So just whatever they've been thinking in mostly. So do you think in kilometers or meters? That will tell you a lot about the physics you do. But the reason why knowing the scale of your problem is important is that it makes your life simpler. For large scales, you can neglect all of the small scale physics. For small scales, you can almost always neglect the large scale physics, right? So those long equations that are like, oh my God, what in the heck is a possible solution for this? We can simplify them. And so trying to estimate those scales is important. The other thing to think about is that in heliophysics, there's a very small set of differential equations that you see over and over and over again. The diffusion equation is one of them. And so you no longer need to know how to solve this partial differential equation. You can jump right to the solution by just looking at it. Oh, there's a Laplacian and a time derivative. That's a diffusion equation. I know it's going to have some sine e to the I, right? It's just going to have some, just tell me the boundary conditions and I'll tell you what the actual solutions are. We see things dn over n. So the time or the rate of change is proportional to the quantity. That's an exponential, and that's why we have exponential fall-offs and density. And wave equations. Everything is a wave. We talk about plasma waves and MHD waves and electromagnetic waves. We see this whole set. Maxwell's equations are wave equations. So I don't even need to solve Maxwell's equations anymore, right? I know it's a wave solution. So I'm going to have some e to the I omega t, right? So as a physicist, try to recognize, oh, this is a diffusion equation, or this is a wave equation, and then everything simplifies. And if you see a long equation, the first thing you should do is get the name of that equation. And there's often a lot of different names that we call them Navier-Stokes equation, or They could be in different forms, a Lagrangian or Euler or whatever, but they have distinct meanings. And, you know, is it advecting with the flow or whatever? Memorize those, because then you can read a description, highly mathematical, and just that one little Navier-Stokes equation. Oh, I know the solution to those. That's what I do. I'm a plasma physicist. And so don't be too intimidated, because you see the same equations over and over and over and over again. So we'll actually go through the same equations. And it's what I find interesting is that I've been able to get funding from NSF and NASA from each of their different subdisciplines, the helio, the magneto, and the iono. And so when I always find it interesting when I'm classified, oh, Mark's an ionospheric physicist. And it's like, oh, awesome. Because I think of myself as a helio magneto iono person, right? So but I'm a physicist, not a chemist. Chemistry, and I apologize in advance. I know that there are some people who love chemistry, and there are chemists. I am not one of them. And so when you get into, can you see, you don't see slides. Is that still true?
No, we see them now.
Okay, good. Chemistry is hard. And if you look at a IT model, ionosphere, thermosphere model, there's going to be pages and pages and pages of chemical reaction equations as part of that model. And it just becomes overwhelming in trying to break something apart. And so, but we'll go through it. So why are there ionospheres? Let's see, type in chat. What is an ionosphere? What's the definition of an ionosphere? An ionized atmosphere, a sphere of ions. Awesome. A plasma, charged particles. Awesome. So an ionosphere is essentially a part of an atmosphere that is partially ionized. And so what is needed to make an ionosphere? And it would be great if you raise your hand and unmute yourself. What would be something necessary to have an ionosphere? Pauline, yay.
Some sort of energy or process to do the ionizing?
Yes, you need to have some type of energy or process to ionize. What else do you need? And you kind of answered it already, Pauline, at the end. You need something to ionize. So I need some neutral gas. And so 10 million points, Pauline. So you need a source of energy that will be able to knock a electron out of its atom. And so for ionospheres, that's almost always photoionization. So essentially the EUV, the extreme ultraviolet and X-rays from our star, the sun, comes down, and we have a bound neutral atmosphere. A pressure gradient is set up. We have a high pressure at the surface of the Earth and very low pressure in space. And so there's a pressure gradient force trying to blow the atmosphere out into space. Why do we still have an atmosphere if there's this huge pressure gradient? Go ahead and type it in chat. Gravity, yay. So we have hydrostatic equilibrium, this balance between gravity and this pressure gradient. And so why does the moon not have an atmosphere? Because the gravitational force is not sufficient to bind any type of neutral or ionized gases in its atmosphere. So when you talk about ionosphere, you cannot neglect gravity. So one of the first things that solar wind people do is, and magnetosphere people, is get rid of gravity. You can't do that for an ionosphere. And you also are talking about ionization, and ionization can be species dependent. The ionization potential for different atoms and molecules can be different. And then also the recombination, essentially the merger of an electron and an ion. So there's a lot of ways of thinking about the Earth's ionosphere. You can think about how we are actually able to observe it. So some of you are looking at incoherent scatter radars. Some of you are looking at optical instruments, doing rocket flights, satellite data. We can think about the neutral gas, which we call the thermosphere, above the mesosphere. And these yellow lines essentially show the temperature profile with altitude or height. And you can see that the Earth's temperature profile has different kinks, that in the troposphere, temperature decreases with height, in the stratosphere, it increases with height, in the mesosphere, it decreases with height, and in the thermosphere, it increases with height again. The thermosphere is the region where most of the extreme ultraviolet and X-rays flux from the sun is absorbed, and the densities are very low, so collision frequencies are much less. And so the hottest temperatures in the Earth's atmosphere is in the thermosphere. And so the Greek word for heat, thermos, gives that away. But you can also see that there's a factor of 2 difference between solar minimum and solar maximum in the thermospheric density. So when you look at the sun in EUV or X-rays during solar minimum, it's dark. There's very little active regions. During solar maximum, the surface can be much brighter. There's a lot of active regions. And when you have eruptions, flares, and coronal mass ejections, the EUV and X-ray flux can many orders of magnitude change. And so we can get a lot more energy into the upper atmosphere during these active events. The ionosphere is divided up into regions as a function of altitude, the D, E, and F region. The F region peak, somewhere around 300 kilometers, is the densest part of the atmosphere, and it has about 1 million particles per cc. Yes, Nick.
So I just wanted to make a quick point about a point of confusion that we regularly run into, is that the thermosphere and the ionosphere occupy the same region, right? And they're intermixed with each other, and we separate these ideas out. That the ionosphere just talks about the ions, and the thermosphere is. I'm always a little confused as to whether ionosphere physicists think of the thermosphere as just the neutrals, or whether it's the neutrals and the ions altogether. But usually it's the people who do the modeling, it's TIGCM because it's thermosphere, ionosphere, electrodynamics, so that they're tied together, and they have to be tied together in order to work. So,
yep. And so, yeah, so the ionosphere is co-located with the thermosphere, and it's essentially the ionized region of the thermosphere. So essentially the photons from the sun and energetic particles from space can come down, bang into a thermospheric neutral, and suddenly it becomes part of the ionosphere. And so since magnetic fields are king, do thermospheric physicists worry about magnetic fields?
Are you asking me or are you asking the class?
No, I'm asking the class. Yeah, and there's no rhetorical questions. Type it in the chat or unmute. So why would the thermospheric community worry about magnetic fields? Anybody know what the equation for Lorentz force is? Right, you remember that right-hand rule. So Q, you need to have a charge particle to feel that magnetic field. So why would the thermospheric community worry about B? Yep, so you guys are way ahead. It's it depends. You could say no because they're neutral, but if you dive deeper into the physics, as many of you have already mentioned, the neutrals can have collisions with ions, and the ions are being controlled by the magnetic field. And so that magnetic field motion can actually drive some of the dynamics of the thermosphere, not directly, but through collisions. And then, of course, you can have electromagnetic coupling between different regions as well.
And do you see Kushek's question in chat?
Let's see.
Which is about, it looks like there's a little bit of separation in the density variability at very low altitudes, though I think that is a function of the plot rather than the actual physics. But
yeah, I agree. I don't know if there is there is not a tropospheric temperature gradient difference due to the solar cycle. So I think they're just trying to keep those separated. Okay. And how big of an effect is this since the neutrals dominate in the thermosphere? So in terms of the dynamics of the thermosphere, Pauline?
Yeah, just the extent to which, say you're writing a thermosphere model, how many, like how much is B gonna have to figure in your equations and how much can you just leave it out?
Yeah, so it's again depends on what scale sizes you're going to be looking at and also what regions. So a lot of the big dynamics happen in the polar cap, which have the vertical field lines and also the convective motion due to the Dungy cycle. And so you could, it's tough to neglect magnetic fields at high latitudes. And even at the equator, there's dynamics, electrodynamics that can essentially entrail the thermosphere. The other thing is that when energy is deposited into the upper atmosphere, let's say due to a flare or joule heating in the auroral zone, a lot of that energy, it gets picked up by the thermospheric particles, so they're not ionized. And then that energy can propagate, and that energy propagation, is a temperature gradient, so that can set up dynamics. But for energetic particles and charged particles, where that energy is deposited depends on the magnetic field. So it depends, as in most things. If you actually do the calculation looking at what the relative number density of ions to neutrals are in the ionosphere, even in the F region peak, neutrals dominate. So the thermosphere by far is orders and orders of magnitude more dense. So in terms of mass density, the thermosphere is king for a lot of the processes. So again, in your conceptual framework, you notice what is the curriculum of the Heliophysics Summer School? Essentially, we've been dividing up the lectures by region. We started with the sun. We went through the solar atmosphere into the corona. We went from the corona into the solar wind. We thought about some of the characteristics of, in terms of energy and particles and composition, temperatures, densities. And then we've moved into the magnetosphere and the ionosphere. And for the ionosphere, we can divide it up into ionosphere, thermosphere. I've already talked about the polar region, equatorial region. We can think about processes. So what are you studying in terms of waves, wave particle interactions? Thinking about the chemistry of recombination and ionization. Again, so follow the money, follow the energy and momentum. What's carrying information from one part of the system to the other? In the ionosphere, we have to worry about chemistry because we could have exothermic and endothermic reactions, and we can have actual transport of different chemical species and excitation of different chemical species that will change the energy density of different regions. And so, we also divide up into techniques. So I am an ionospheric physicist, and I use Fabry-Perot imagers, or I use ionosounds, or I proposed an instrument for GDC, the next ionospheric mission, to do in situ measurements. And then your technique could be, are you a modeler? Are you a data analyst? Are you an instrument builder? And you could start thinking about empirical models, physics-based models. So there's all these little subdivisions. I'm an ionospheric modeler that does first principle physics models of the high latitude electrodynamics, right? So we have all of these different ways of organizing. So when you see a new term, see if you can fit it into it. Is it a region? Is it a process? Is it a technique? So almost everything we talked about last week essentially got rid of every term on the right-hand side of the momentum equation. We just had ideal MHD. We assumed everything was in equilibrium, force-free models, current-free models, potential models. So we had all these terms for essentially saying we're getting rid of sharp gradients and we're getting rid of some of these force terms. Ionospheric physics, and again, depending on, particularly if you're looking at DE region or F region topside plasmasphere, you can't get rid of the terms because collisions, neutral ion collisions can play a big role. And that density also impacts your recombination rate. Is it a molecular or atomic species? What type of excited atoms or molecules are you looking at? You have to worry about radiative processes. And really the only people who are doing radiative processes are the folks that are looking at the lower corona photosphere, you know, these flaring processes and the Chianti codes of looking at the spectroscopy of what's going on to try to understand processes. For almost all of the corona and the solar wind and the magnetosphere, we can pretty much neglect radiation, but not in the ionosphere. The other thing that if you talk to a meteorologist, somebody studying the neutral atmosphere of a planet, it's almost always in hydrostatic equilibrium. So essentially hydrostatic equilibrium, there's no vertical velocity, everything's horizontal. So you have to add Coriolis forces and stuff like that. But for the ionosphere, there is vertical motion, there's outflow, upflow. Even at the low latitude regions, there's heating. We talked about the Starlink event. Energy was dumped into the thermosphere. The thermosphere heated and reached a new equilibrium. But in that transition between one equilibrium to the next, you actually moved mass to higher altitude. And then Carol was talking about, electric fields and Mark Chung electric fields that essentially they're frame dependent. So physicists like simple things. Let's move into a frame where the electric field goes to zero. So essentially we don't think about electric fields in a lot of the heliophysics contexts. In ionospheres, we think about electric fields a lot, electric fields and currents. So I posted Eugene Parker's paper as part of the conversation that Carol Shriver mentioned about the different paradigms of thinking of J and E versus V and B or U and B. And for MHD, for fluid magnetohydrodynamics, U and B is king, because you can move into the frame and get rid of E. And in one sense, J and B are the same. Right? I have curl B equals mu naught J. Which came first, the current or the magnetic field, or the magnetic field or the current? You have to have both. But for the ionosphere, to actually understand the dynamics and the coupling between the different ionospheric layers, we almost always think about electric fields. So one of the equations we introduced in the magnetosphere section was the continuity equation, but in that side, I essentially had dn dt plus the convective term, the del dot B equals 0. And so I can't do equals 0 in the ionosphere. You are almost always taught you can't create matter. So if I have stuff, it's either compressible or incompressible, but I'm not creating it. For an ion, I can create it. I could have nothing there, the sun comes up and boom, EUV flux photoionizes it, and suddenly I have Ni. So I see this change in Ni. I didn't have to move anything in it. I literally created it. Sun goes away, recombination takes over, it starts going away. So ionosphere, not even the continuity equation can I separate it. So this looks pretty easy. There's only 3 ways I can change anything. It's sort of like your bank account balance. $, DT, how can I change it? I can earn it, I can spend it, or I can get a gift, Venmo. And that's it. But how many different ways can I spend my money? How many different ways can I get money, right? So see if you can type in the chat some of the source or loss terms for ion density in the ionosphere. We've talked about EUV photoionization. What would be another source term? Or okay, so I can have that drift, and that drift is part of the transport. So I can move plasma. So collisions can also move plasma. If the collision is high enough energy where I can either excite or ionize or even dissociate, then I can have a change in source terms. All of these terms are going to be altitude dependent. So that's not a unique source or loss term in itself, but that adds to the complication. So besides photoionization, I can have particle collisions. So I could have impact ionization, right? We talked about these cosmic rays and these ground level events. I can have a 10 to the 23 EV cosmic ray proton slam into the top of the thermosphere. And it has so much energy, it's not only going to ionize whatever it hits, it can actually break it apart at the nuclear level. So I can slam into this thing and break apart the nucleus. So I'm going to start having gamma rays and muons, pions, kaons, all these other things. But I have so much energy, there's still energy left over. So that fragment can slam into another one, slam into another one. So I get this shower, this cosmic ray shower, that one cosmic ray can lead to, you know, millions and millions of particles going throughout the atmosphere. For loss, we have, of course, recombination is a dominant loss that we have to worry about. And recombination depends on altitude because it often depends on what type of species or composition. Molecular ions have a higher recombination rate than atomic. So that's one ratio that people often talk about in ionospheric physics, is the molecular to atomic ratio, or atomic to molecular ratio, because that tells you something about the lifetime of the ions. And so since these are also ionized, they're going to be line tied to the magnetic field. And since the magnetic field is co-rotating with the Earth, we essentially are bringing a flux tube into sunlight in noon at the highest flux, into dusk, sunset, night side. So we have a diurnal variation of transport that makes the sources and losses turn on and off. So to a really good approximation, what is the solar wind made out of? What element? Protons, or H plus, hydrogen and helium. So in one sense, unless you're a Sioux lepre that are looking at some of these very minor species, we can think of it as a electron, plasma, proton fluid. It's 90-something% protons and on average, you know, less than 4% helium and fractions of a percent everything else. When you talk about the ionosphere, the Earth's ionosphere particularly, you have the main atmospheric constituents, N2 and O2, that get broken up into N and O. And then they can have some chemistry. So we have NOs, molecular oxygen, molecular nitrogen, atomic nitrogen, and atomic oxygen. And so we have both molecular and atomic species and different ones. This vertical profile and density, as you see, we have this F-region peak around 300 kilometers. And you see that the ionosphere is dominated by O+. So the major ion species of the Earth's ionosphere is O+. What would you think Mars's ionosphere, what its dominant species would be? Or Uranus, or some exoplanet? It would probably be the ion species that's the dominant neutral. or some product of a dissociated molecular. So Earth has a lot of oxygen in the atmosphere, and so O+ dominates. You see at this altitude where the H+ or the protons cross over and become the dominant species. It's about 1,000 kilometers. Anybody know the name of this transition? When you go from O+ to H+, you go from the ionosphere to what region? The protonosphere. Yep. So that's the old name. And that's why. What do we call it now? So an exosphere is usually limited to neutrals, is sort of the classic thermal escape mechanisms of the gene's escape of neutrals. That's right, 5 million points, the plasmasphere. So we have a transition from the E, D, E, and F region, the topside ionosphere, which has this sort of exponential decay. And then we hit a transition where the H+ starts dominating, and that's the plasmasphere. And you notice that due to loss, the bottom side ionosphere essentially really goes away, where we have densities of 10 to the 4, 5, and poof, they drop down to 10 to the 2, 3s. And it's essentially because recombination is proportional to density. So background density, you're going to have a lot of collisions, so you can have a lot of opportunities to recombine. And so as you go up in altitude, the recombination rate goes down. And so the topside ionosphere still has very high densities, even at the night, because the recombination rates at that time are essentially on the order of the planetary rotation rate a day. So the sun can set, I have no more source, but my recombination times could be many, many, many hours. And so I still have an ionosphere when I come back. Okay, so type in chat, what's the name of the equation that describes transport? So that transport in the continuity equation, we can think of that in more detail. What determines transport? Yep, so it often describes convection, but Newton's equations, and which one in particular do we see over and over again? Second law. And what do we call that in the MHD equations? We have the continuity equation, energy equation, and what's the dv, rho dv dt, the momentum equation. Awesome. 5 million more points. So I think you've seen the momentum equation pretty much every slide. So we study dynamics. People are interested in things that are changing. Imagine if we lived in a steady state universe, nothing changed. Boy, that would be boring. And so usually in every field, we look at changes and rapid transitions or equilibrium transitions or a change of state or an event we really like. So when you think about regions and processes as a way of organizing heliophysics or any type of human endeavor, the other way you can classify things are events. What are the important events that characterize that region? So we can talk about solar flares and coronal mass ejections. And so I could ask you, compare and contrast a flare and a CME. How are they the same? How are they different? Compare and contrast a geomagnetic storm with a substorm. Compare and contrast a kink instability with magnetic reconnection. Right? we can think of these processes and these events, these things that have a time equals 0. So if you're a cardiologist, you might be interested in heart attacks, or if you're an economist, you might be interested in recessions, right? It started here, and what can we do to get out of the recession, or high inflation started peaking, or whatever, right? We look at these transitions. And so the momentum equation, the F equals ma, those are the forces that give rise to big DDTs in motion, right? They accelerate things, they move things, they break things apart. And so when you think about ionospheric transport, we've had it typed in the chat already, E cross B, and that E cross B, depending on where you are, is going to be either horizontal or vertical. And so a lot of dynamics go into that. So here are the equations again, but now it has a little bit more. So here's your d rho dt, mn, as a function of species, your convective term, your source and your loss. So transport, source, and loss. And each of these can be as a function of O plus, NO plus, N2 plus, right? I could have a whole series of continuity equations. Ideal MHD essentially takes all of these and says it's a single fluid. I don't have an electron and an ion fluid. I just have a single fluid, right? But I could have a 2-fluid MHD. I could treat ions and electrons differently. I could have a multi-fluid MHD equations. I could think about O plus and H plus and electrons as three different momentum equations, three different, right? And so multi-species, multi-fluid, they have different assumptions, but essentially are the way to break it up. So here's my Newton's second law, rho dv dt. So I have this convection advection term, my pressure gradient, gravity, my electromagnetic forces, and some collisions. So this is a collision velocity, and it's proportional to relative motion of different species. So I could have collision frequencies between electrons and ions and electrons and neutrals, right? I could have all different types of collision cross sections. And then I have my energy equations. And so these set of equations, 3 equations, continuity, momentum, and and energy. But my unknowns are 4. So I can't solve these. So I almost always have to have a equation of state that relates one of my variables to another variable. So I can close the equation, have the same number of unknowns. And so we often will use an Ohm's law or an ideal gas law or something like that to close the equation. But for the ionosphere, if I consider a strong magnetic field, so essentially close to the Earth, only 100 kilometers off or 300 kilometers off the surface, I can start thinking about this cyclotron frequency. My ions are going to see that magnetic field, and so they're going to be rotating around it. So if they have a velocity perpendicular to it, they will be in the cyclotron motion. So that is going to give me an inherent time scale and length scale. And so then I can compare that to a collision frequency. Am I able to go all the way around my orbit before I bang into something, or will I bang into something before I can go all the way around? And if I bang into something, then my momentum is a scattering process, and I get scattered in 4 pi. And so suddenly I can now have a different velocity, different, and so this cyclotron motion, cyclotron frequency versus collision frequency is a key term. But if I look at a strong magnetic field as essentially I'm essentially saying my collision frequency is my cyclotron frequency, that's going to give it. So if I look at this, it essentially defines my motion. I am trapped on a flux tube. So in the ionosphere, we're in the limit where B is large, wherever the magnetic field is going, I'm going to go. So that's one part of the transport. So depending on my latitude, I'm going to be pulled across the polar cap. So if I look at an Amy convection pattern or a super darn radar pattern, I'm going to see this convection. The flux tube is being pulled by the solar wind. I'm pulling the footprint with the plasma tied to it across. But I also can move along the field line. So now I have to rewrite my equations of motion, but now instead of thinking about them perpendicular to the field line, I'm going to write them parallel to the magnetic field line. So I have my continuity equation, my momentum equation, but now I'm only looking at the parallel components. Same with my energy equation, and I can solve these. And so one of the interesting aspects of this parallel motion is that electrons are, for same energy as an ion, are going to be moving faster. So if I have a component of my velocity for an electrons along the field line, it's going to start streaming along that field line. So I'm going to start separating electrons from my ions. What happens when I have a charge separation? What do I create? If I have a capacitor plate, you get an electric field, 5 million. Yep. And so this was this polarization electric field that Carol was talking about, and Joe Giacalone was talking about, that Parker Solar Probe is trying to look at. Almost always we neglect it. In the ionosphere, we can't. But if you actually look at another way of thinking of solar wind acceleration, not the Parker fluid approach, the real reason why the corona flows out supersonically into the solar wind is because you have energetic electrons that are streaming out along the magnetic field. They set up an ambipolar electric field that pull the ions out with them. So you get this flow out. And so that's one of the other big interesting aspects of the ionosphere. At the high latitudes, the field lines are essentially vertical. I can get outflow. So if you think about the Earth's thermosphere, I add EUV, I'm going to get an ionosphere. And what are the dynamics of that ionosphere? It's essentially just going to be temperature gradients. Day side's hotter than the night side, so I'm going to set up wind patterns, and I have rotation. If I add a magnetic field, it gets a lot more complicated. Not only do I have temperature gradients and pressure gradients, I now have pressure gradients along the magnetic field. I also can have these electric fields set up that give me an E cross B drift that's vertical at the equator. At the poles, any E cross B drift will be horizontal. At the equator, it's vertical. So now I can have vertical motion of my plasma. And now if I couple it with the solar wind through magnetic reconnection into the polar cap, I can get all of this two-cell convection, I can get Joule heating, I can get ion outflow, field line currents, Joule heating, dumping thermospheric energy into the thermosphere to set up these winds that can go all the way across the equator, a lot of dynamics. And so now I throw in a storm. Everything that's at high latitude now moves to lower latitude, and everything in the equatorial region gets bigger. So essentially, I'm mixing up all of these dynamics on top of each other. So if you're an ionospheric physicist, which part of this system do you study? So there are a lot of people who study the equatorial ionosphere. There's a lot who study the mid-latitudes, a lot who study the polar cap or the auroral zone, right? So, and the reason is the events, the substorms and the storms get really complicated really quick. And so we often will focus on one diagnostic or one region or one type of event. sudden stratospheric warming effects on flows. So just to finish, an ionosphere is any gravitationally bound atmosphere that has energetic particles or photons present. And the density structure depends on source and loss, incoming electromagnetic, particle flux, the neutral density. So planets could have very different scale heights, compositions, temperatures, gravities, chemistries, transports, presence or absence of magnetic fields, electromagnetic coupling, dynamos, et cetera. You have all of these complications. And so for the Earth, you almost can't neglect anything. And so the physics of the global ionosphere, thermosphere models, the codes are hundreds of thousands of lines long. So, okay. Well, does the moon have an ionosphere? So put a thumbs up in the chat, yes or no. What do you think? What do you need? So we got a no. No. So how would you know? How would you actually probe it? We could go there and try to measure it. But how would you know it's gravitationally bound? And what would be the dominant species? What's weird is the moon does have an ionosphere, but it is weird. So we discovered during the Apollo that radio waves got refracted through the ionosphere of the moon. So when the Apollo was on the other side sending a radio signal across the limb, we saw the refraction, which requires an ionized medium. So there's an ionosphere. But it took until 2011 before somebody figured out what is it, because the exosphere is not gravitationally bound. Mostly it's all going. So you wouldn't, even if you had charge exchange or photoionization, the charged particles wouldn't stick around. They'd get picked up by the solar wind and taken away. But Stubbs showed that the dust in the lunar regolith can become charged and suspended above the surface of the ionosphere. So essentially you have the supermassive ion, a macroscopic chunk of silicate that acts like a plasma. So dusty plasmas is another area of heliophysics. And think of the momentum equation. Now you're dN dust. And what is the source and loss of the ionization of the dust around a comet or an asteroid or a volcanic moon? So ionospheres are very cool because that's where we live, but have a lot of physics. Okay. So I think we're now, if you have any questions or office hours type of questions.
Yeah, so thank you, Mark. That was a grand tour that is a preview of what we're going to be talking about over the next couple of days between the lectures on magnetospheres tomorrow and the lectures on ionospheres on Wednesday. The lectures, the magnetosphere lectures tomorrow will be Christine Gabrielis talking about the magnetosphere data, and then Slava Merkin talking about models of the magnetosphere. Slava, just as a reminder, is one of the heads of one of the drive centers, the CGS drive center, which I can't remember what it stands for, but it's focused on the magnetosphere. And I'm not sure where Christine is. Do you remember, Mark?
She's at Aerospace Corporation.
Oh, right. Slava sent a little bit of a reading assignment. So from the text, chapter 3, of course, know all of your MHD, right? So, but we've been doing some of that. So, he suggested chapter 5, but I pared that down to the sections on the magnetosphere, though you might look at some of the other sections on there. and then section 6.1.2 on geospace stubstorms. But you'll also notice that Carl paired that with the flares and CMEs section, so that you should keep in mind that flares and CMEs and geospace substorms and storms have a lot in common in terms of what they're doing. So just something to keep in mind when you're doing that. So so I think you can. There's some doable, easily doable reading in the suggestions that I put into the time zone workgroup channel. So good study exercise to identify the name and term of each momentum equation. Oh yeah. So that's an MHD study exercise, you're saying.
Yeah, but you're going to see the momentum equation for the rest of your career. And so having a good intuitive sense about when you can neglect terms.
Each term in yes, and that's actually what part of Carl's book is. So that section breaks those pieces down into their individual components and has different comments on each of them. So I think you should probably go back and review that. I think that's a good idea. Any questions or comments from what we're doing going forward? Anything from Maggie about logistics or anything like that?
I don't think I have any updates, no.
Great. Nope, that's good. This Zoom logistics is pretty easy. All right. So with that, we're done with the programmatic portion of today's, the scheduled portion of today's. We'll move into Mark's office hours, and I will be around too if we have questions regarding the lab.